Hi everyone, thanks for joining this lecture, and thanks for David for putting up this great course. I saw the series of talks. It's a really stellar program, so well done, David. I was told that it's better if I first present for about an hour, and then questions afterwards, because it's also recorded, so it's easier than to package that. So unless you have really clarification questions, maybe we can keep the questions to the end. So I'm going to talk to you today about trying to understand and model human social foraging. And foraging is a very basic property of any organism, and it's the ability to find and extract resources from complex environments. In the case of humans, our ability actually to forage across very different landscapes and in different social settings has also been thought to be one of the drivers of our success of a species, and even things like brain size are thought to be also evolved from actually our ability to engineer and find our ways in such different environments and with such different challenges. So foraging, especially in humans, is extremely diverse in scope, as unseen in other organisms. And when you think about foraging in the real world, if you look at some of the characteristics, you probably realize that there's a very complex choice environments with many decisions to take. Space is very important. Of course, human decision making in real world environments takes place in a spatial context. There's probably going to be interactions between your behavior and environment. The behavior that you apply might give you different returns in different environments. So you need to tailor your behavior to the environment you're in. And many of these processes can take place at different scales. For example, foraging, in the beginning of the day, you might need to make a decision: do I go to location A or location B today? So you have to make a large-scale decision on where the general foraging area you go. But then once you arrive there, of course, there are a number of micro decisions you need to take on a much different scale. And if we look at foraging studies that are done in the lab, typically with humans, we see that actually much of this reality is stripped away. So these are very simple choice paradigms. They are typically not spatial. There is not really an interaction between behavior and environment. So although there's a lot of literature on human foraging in the lab, it probably cannot tell us so much necessarily about what is actually happening in the real world. And this is in psychology, this is known as real world and the lab dilemma. Where you, for example, foraging, you have on the one hand very highly constrained lab environments, which can become more and more immersive and realistic, all the way up until trying to actually understand human behavior in the real world. And in psychology, this is actually a very big divide between, of course, the lab and the field. And I mean, this is a debate that's been going on for many decades. But you still see in many areas of human psychology that the step towards actually trying to study these processes in the real world is often not done yet. And as a result, what we kind of have ended up with is that in the lab, many people study the cognitive processes that are happening inside our brains, right? So here we are studying, how is memory coded, how does evidence build up, and all of these, cognitive processes are highly detailedly approached and quantified in the lab. But if you then look at real world studies, actually people kind of forget about cognition, and they really mostly focus on descriptive statistics of what happened of a series of decision-making processes. So if you look at foraging studies from the wild, then it typically will be at a very high kind of coarse level, they're very descriptively about how the percentage of time people have done different things or the total amount of food that they have gathered. But not really kind of trying to tap into the decision-making and or the cognitive processes driving these decisions. So we are trying to kind of partly close this gap and try to actually bring cognition more into the field. And we feel that this actually at the moment is a good time for this. So there's a number of advancements that are happening on the technology end that allow us to, in more and more detail, actually quantify what the individual doing, what information they are exposed to. And for some examples, we're getting, of course, much better at actually identifying where individuals are in time and space. These wearable eye trackers, for example, allow us to quantify, the information individuals are extracting in real-world environments. And then more and more devices to, for example, quantify the internal state of an organism or of a human, right? So we can actually, all these devices can actually, quantify what certain behaviors are doing to an internal state, or how internal state is driving behavior, right? And all of these things are, of course, embedded in this gray circle, the choice environment. We're also, of course, getting much better in actually quantifying choice environments of individuals in the wild. So what other options that they can choose from. Because, of course, only if you can describe the environment, you can actually understand what are the options that an individual actually has to choose from. So these technological advancements, I think, help us to actually try to bridge this real-world and lab dilemma. And PhD student of mine is he's writing this review. It's not out yet, but we make on one hand the argument that because of all these technological advancements, we're getting closer and closer to these possibilities. And then the other developments that are happening is that there's a number of statistical tools becoming available that also allow us to actually make inferences from very noisy real-world data. So of course, if you do a lab study with humans, you just ask them to press a button if they make their decision, and it's very easy to quantify their decision-making process. But of course, in the real world, you don't see the decisions so obviously, right? You get noisy data, and from this noisy data, you need to actually infer what decisions did they make, right? And I'll give examples of this later on, in case this is not very clear yet. So that's the first inference problem. And we're, of course, there's a whole range of tools that is becoming available to actually start to help us actually to identify when an individual actually makes a decision, right? So what is the moment in time that they make a decision, and what was that decision? And then from these decisions, we want to ultimately get at the latent processes that drive these decisions, right? So what are actually the factors or the cognitive processes that lead individuals to make certain decisions? And again, there's a whole, and I'll touch on some of these mechanisms that we can tap into and start trying to really understand human decision making in much more complex choice environments. So kind of with this broad framework, I want to talk to you today about four different topics on social foraging. We'll see if we'll manage to get through all of them. And in each of these topics, I will start with a lab study where we first kind of study these processes in a virtual setting or in a lab setting, and then I will move to the real world and try to also make connections between how to study it in both environments. So we're going to start with how do individuals decide where to forage, which batch to select. And here this is work led by Charlie Wu. Here we did an immersive foraging game in Minecraft where 4 people in groups of 4 were competing against each other to find as much resources as they could. So people could destroy these blocks. And for example, these fireworks that suggest, so if as soon as you find something, a firework set off. So that is a public signal that, hey, there's actually somebody found something. So you can hear, of course, although this is still a game, you can already imagine that it has quite a lot of real world features, right? So you have your visual attention. You have limited visual attention of where you're paying attention to. You have to orient yourself towards others if you really want to see their information. It's very spatial, right? So you have to make a decision, am I going to forage close to others? Am I going to actually maybe go far away from other individuals? So it has already quite a lot more elements than the typical human foraging study that is done in the lab. And plus it's fun to do things in Minecraft as well. So the design that we had, so people started with an interactive tutorial, and then in different orders they performed either solo rounds where they were foraging by themselves, or they were foraging in groups of 4, so they were controlling one avatar and there were 3 other avatars controlled by other players. And then we manipulated the resource environments that they faced, either random environments, and in these random environments the resources are completely randomly distributed. So there's no pattern there. So it means you cannot really learn anything about the spatial distribution of rewards. So the discovery of a reward locally doesn't actually tell you anything about whether there are resources more likely to be close by or far away. But then the other environment that we tested was a smooth environment, and here, of course, you can see that the resources, so the black boxes, are actually clustered. So in these environments, of course, it makes you can actually learn something about the resource distribution, and you can also use, of course, the discoveries of other individuals to guide your choices. So that was the design. And with the help of Ben and Kyle, what we basically did, we replayed all events, and then we automatically quantified how many pixels of the different types of information people have were actually visible at 1 second or 60 hertz resolution. So, for example, we could automatically quantify the amount of fireworks visible to a player in the game at all times, or the amount of other people that were visible any amount or in time, and whether these other people were successful or not. So it gives a very high resolution data set of the visual information that people were exposed to. Admittedly, we didn't do eye tracking here, right? So it might be that people were actually paying more attention to some parts of the screen than on others. So that's not something we did here. But it is, well, I guess it's reason to assume that you could see the whole screen at all times. So that seems to be reasonably okay. And then one question that we asked is, okay, how do individuals decide which block to destroy next? Where do they forage? And for that, what Charlie did is it's visualized here. So we're now focusing on this individual, which is gazing this direction. And then we're looking at what are all the different cues that this individual has to their disposal to inform their decision. You can think about a number of asocial features that they may use to determine where to go next. So one thing, for example, which seems reasonable, is locality. So if you're at a certain location, you're probably much more likely to destroy blocks close by. So that means that if the individual's here, the blocks very close by, they get a very relatively high weight, so indicated here by yellow, and blocks very far away, they get a very low weight. So they are relatively unlikely to be destroyed based on the feature of locality, if that is playing a role. And then you can do the same for visibility. So are blocks that are in your visual field more likely to be destroyed next? And then a more interesting one perhaps is rewards. So this is a mechanism called spatial reward generalization. That means that if you found something somewhere, then you're more likely to actually stay there and destroy something close by. So that's therefore here kind of again the yellow close by. But you're more unlikely to go further away. But if you did not find something, this prediction reverses. So imagine you didn't find something, then you actually expect to not forage locally, but to actually move long distance and skip blocks. Because if you didn't find something, you may infer, okay, that means this is a resource poor area, so I better make a long range displacement. So that's asocial features. And then we can also, of course, think about social features. And here we Charlie looked at other individuals that were successful, that we call social plus. So you see another individual and you also saw that they were successful. So you actually before making your choice, you saw a firework coming from that direction. And the other thing we tested is there a general social attraction? So are you also attracted to others who are not successful, right? So just do you want to stay close to others in general, independent of their success? And so in the modeling, we then tried to tease apart the importance of these different possible cues people could use as a function of the environment they were foraging in. Remember, we had a random or a smooth environment. And let me walk you through some of the results. So you see here that locality played a role in all treatments. And see, so this is the group treatments in different environments, and this is individuals alone. And you see that in all these conditions, individuals were more likely to forage close by. No surprise there. Again, people also were more likely to destroy something in their visual field. Also trivial almost. Here it becomes more interesting. So this is this reward prediction. So did people actually generalize their discovery of resources to the nearby environments? And here we see that in smooth environments, individuals indeed very much did so. right? So here in these smooth environments, both in group and in alone conditions, they actually, when they found something, they stayed local, but if they were not successful, they made long-range displacements. So they adaptively tuned, you know, how they dealt with the discovery or the absence of a resource as a function of the general environment they were in. And maybe to a note, so people were also it was communicated to them in what kind of environment they would be foraging that round. So that was not something that they needed to learn. They were actually told, okay, now you're going to a round and resources are random, or now you go in it's smooth. Of course, you can do a different experiment where you not tell them and then see how that learning process works. So were people attracted to successful other individuals? Yes, but it differed quite strongly on, again, the environment they were in. So in these smooth environments, people were much more attracted to successful others, as in the random environments, which is adaptive, right? Because in a smooth environment, if you see somebody discovering a resource, that's actually predictive of, you know, resources being present there. Whereas in a random environment, you should actually not go to other individuals, even if they're successful, because it's unpredictable where the resources are in any case, right? So you should actually not use social information or social success information. But we still see that people have, even in this random environment, they have a slight tendency to actually to go to the location of other individuals being successful. And yeah, finally, people. Sorry about that. People were not attracted to unsuccessful individuals. And the last thing on this is that of course, here we are presenting them as rather like static effects, but that is actually not the case. People actually also tune these weights depending on the experience they have in the game. So, for example, here you, for example, see that the longer it takes since you didn't discover anything, the blue line actually goes up, meaning that you're more and more likely to start copying successful individuals. So if you yourself are not managing to find something yourself, you start actually paying more attention to the individuals around you. So yeah, just to say that these processes are not static, but people actually adjust along the way, depending on their experiences. Okay. Normally I would ask for questions, but I think we'll move on. I hope it's not going to be too dense and too much. So let's now try to ask the same question in the wild. How do individuals decide where they go and forage? And for that, I'm going to bring you to this study system that we're, since a couple of years, are trying to understand. And this is ice fishing in Finland. So ice fishing was traditionally an important subsistence style of humans. And from this subsistence style evolved these competitions. And in many Nordic countries, they organize these competitions where people will go out for a couple of hours. They try to catch as much fish as they can, and after a number of hours, they come back. Their catch gets weighted, and then the highest, the people with the best catches win the game, win prizes. These people we are studying here, it's quite crazy. They will happily do like 100 of these competitions during a winter season. So they're actually, this is very passionate about this sport. It's very dear to them. It's actually quite a important part of their culture. And yeah, you can of course already see maybe some similar elements here. Are you paying attention to where other individuals are and if they're successful or not? And how do you cope if you catch something or not? And this is, for example, during the competitions, you see here a cluster of individuals, or here you see, for example, a group of individuals. You see also some individuals sitting alone, and it looks like a completely white landscape, but there's more to it than perhaps meets the eye at the first glance. So we put a GPS tracker on all of these individuals, and so we know exactly where they are at each moment in time. So each red dot here is one individual, and what I want to also want you to pay attention to is these depth profiles here. So you here see the bottom of the lake, and you see that this is, of course, it's not a homogeneous bottom, but there are actually depth gradients there. And these ice fishers are telling us that they utilize these depth curves actually to predict the presence of fish. So this seems to be an asocial feature that that foragers in this system seem to utilize, and of course we were keen to test it. So it's a lot of, they spend, I think, about like 70 to 80% of the time really fishing, and then maybe 5% of the time drilling holes, which is quite tough actually, and then maybe 15% of the time they're relocating to different locations. Each individual is carrying a head camera. So here you see one individual that is moving. So this allows us to quantify at each moment in time what the individuals are doing or whether they're successful. So here you see that they start to clear some snow for drilling. So here they are drilling. This ice can easily be 70, 80 centimeters thick. So it's also quite a handling cost. Here you see an individual fishing. They use relatively simple fishing gear. They were just catching fish. Another fish catch. Here they're packing up, and they're moving to the next spot. Yeah, so we kind of at a high level kind of the design that we have here. So we have multiple different individuals, and we studied these individuals at different lakes. So we actually had the same group of around 50 people, and they were tested on different lakes. And then for each individual we have the spatial trajectory where they walked, shown here, and then we know exactly where did they stop and where did they start fishing, and were they unsuccessful, the green dots, or were they actually successful at these locations. And then for each fishing spot, we also of course we have the complete dynamics of fishing success that happened at that spot. So here, for example, is just one illustration. It's an individual that stayed here for about 8 minutes, and then we also, using these videos, we quantified all their individual catches that happened. And yeah, we had around, I'm presenting data today of around 10 days. So each day is a new competition of 3 hours at a different lake, and each day had around 50 participants, and they foraged for around 3 hours during one competition. So you can imagine this is really heaps and heaps of high resolution data. What is nice now is that we can start partitioning the variation that we see in behavior between participants. So are some individuals actually more likely to do A, to use social information, than other individuals? But we can also partition variation according to the environment. So do we see more of certain behaviors, social information use, on some lakes than on others? And what is it then about that lake that elicits this? So I'll come back to that as well. Yeah, so where to forage? So Alex developed a method very similar to the Minecraft example that I showed you, where he tried to predict the movement of individuals, again based on certain features they could use. So for example, success. Were individuals more likely to stay close to the location if they were successful at a spot? Here he also modeled separately loss. So if you actually were not successful at a spot, were you more likely to stay close or to move far away from that spot? Social, are you more likely to go to areas where you see other individuals? Here we kept it actually at a very high level. We're not looking at the capture success of other individuals. We're only looking at the density of other individuals. Once you move to the real world, you often realize that there are some constraints at the level of detail that you can quantify, which doesn't mean these processes do not play a role, of course. And then finally, the thing I described earlier, this lake bed roughness. So these gradients and depth profiles, where you basically either have kind of very flat areas on the bottom, or you have very steep gradients. And people were telling us that they go to these areas with steep gradients. And so this is a visual representation of how that model looks. Maybe as one example. So for example, here you see, here it's easy to explain. For the social feature, the triangles here are other individuals. So that means that locations that are close to other individuals, they get relatively a lot of weight in this model. And areas where there are relatively few individuals, they get very low weights. What Adam then did is Alex did is then he compared the position where people actually went to to 50 randomly generated places they also could have gone to, and then see was this location that they selected actually different from what you would expect based on chance, and do we see that this place that they selected, for example, did it contain more other competitors? So was the social density higher as compared to a random choice they also could have seen? Right? So this is kind of in a very quick and dirty way how the model tries to infer the importance of a feature on site selection. And again, please ask me to clarify if this does not make any sense. And kind of our data contains around 16,000 individual spot choices. So really a new hole that hasn't been drilled by a person. So they had to decide, where do I go and where do I put that drill, right? So it's quite a large number of observation points. Okay, so let us go to the results. So what we find is that, and here the green is the overall estimate across all lakes, and the black dots or bars are the estimates for the lake. And we see here that across all lakes, we see that individuals use social information. So that means that they're more likely than chance to start drilling, in areas where other individuals are, right? So there is social attraction in the system. Individuals look where others are, and where they decide to forage is partly governed by where they see other individuals fishing. This roughness feature played a little bit of a role, but it was not very strong actually. So we didn't find a lot of evidence for that slide, but it's relatively minor. And then we see, unsurprisingly, we see that success plays a big role. So this means that if you're successful somewhere, that means that the next hole you drill is relatively close to that successful spot you just left, and vice versa for unsuccessful areas. Then you're actually, if you experience a loss, or in other words, if you were unsuccessful, it means that you're more likely to actually move away from that area. And this is, I guess, not super surprising. Again, we find interactions between some of these terms, or what's also called conditional weights. For example, again here maybe it's actually easiest. This is the same as in the Minecraft. The longer you go the longer you're being unsuccessful yourself, the more you start actually relying on social information. And the other way around, if you are successful. So if you are successful, you actually start paying less attention to the social density. Then, of course, we can also look at, okay, this is the cues they used, but how good were these cues actually in predicting the resource presence, right? So what is actually the validity of these different features or cues? So we can calculate, for all spots where there was a high social density of foragers compared to when individuals were foraging alone. Do we actually see that spots where more individuals are around, are they actually more? Are these spots also better in terms of how many fish are getting caught? And you actually see a very nice, I think, relationship here between how people are using the cues and how useful or how valid the cues are. So this, for example, means that areas with high social densities are on average more successful. So they have there's a higher resource return catch rate than on areas where there's a low social density. Roughness was not predictive of capture success, and areas that were close to successful other areas were more likely to contain resources, and the other way around for unsuccessful areas. So yeah, if anyone knows of Brunswickian school of thought, this is I think a very nice example of that. So people are actually adaptively weighing these features, it seems. Alex then tried to build generative models to see if we could actually capture some of the key empirical dynamics observed in the system. And he was to see, okay, we identify these features, but if we actually simulate out behavior using only these features, can we recover the dynamics that we see? Because of course it's nice to kind of say, oh, we get certain weights for certain features, but if you can actually also plug in these values in a simulation model and then actually provide a close match to empirical observations, you can have more faith in that these feature weights actually are meaningful. Just as one example, here we have how many spots ago was it that you actually were successful. So 0 means I was successful at my last spot, but 10 means that I have not been successful for at least 10 spots. And then we first looked in the data. What happens to your relocation distance? So how far do you move, and to your turning angle? So how directional are you in your movement? And what we see in the data, the black line, is that the longer ago it was that you're successful, the larger you start relocating. So if I was successful for quite a number of times, then in my next choice I'm going relatively far away for my next drilling attempt. And at the same time, my turning angle also goes down. And if your turning angle goes down, that means that you're moving away, from the point that you came from. The shorter that turning angle. Because if at each point in time your turning angle is again very different, that means you're more likely to stay close from the origin, the place that you started. So we see that very clearly in the data. Alex was also able to actually recover this pattern with his model simulations by only plugging in kind of the behavior that people were, doing a simulation, and basically if I'm successful, I'm going to do X, and if I'm unsuccessful, I'm going to do Y, based on the feature weights that we extracted from the model. Interestingly, this was also mediated by social density, this behavior, in the following way. So. The pattern was most pronounced at low social density, so the yellow bars. So there we see that the longer the stretch of not being successful, the further you move, and the shorter the smaller your turning angles become. But actually, when they're foraging at high social densities, we see that this effect is not so strong. So it's interesting that these patterns that we often think of as being really individual level kind of properties or characteristics, and in this case this is what is called area restricted search. So that means if you encounter something, say local. If you don't find something, you go far away, area restricted search. But we see that there's actually also the strength of this phenomenon is mediated by how many other individuals are actually around you. And again, I think this is not something that people in human foraging literature is actually really dealing with. They're really approaching foragers as single individuals who kind of operate almost in the social vacuum. Like I said before, we can now also see at what causes some of this variation that we see in behaviors. Just as one example, for example, we can now look at do we see any difference in social information use when we compare different individuals and when we compare different environments or lakes. And we see actually that for this feature, so how much you rely on social information, you see that individual variation is actually quite strong. So within this group of ice fishers, we find consistent individual differences in how much they actually use others to determine their site choices. If you now look at individual features, for example, in this case we find that females rely more on other competitors than males. We did not see an effect of age or of self-reported skill. Looking at environment, we see that individuals use more social information in areas where the average catch rate is higher, or also when there's a higher percentage of successful spots. So I mean, it's not something we completely understand yet. It's early days, but I think what is nice is that we can really try to tease apart, what actually drives variation in behavior. Is it environment? Is it individuals? And to me, it's really interesting to see also how these different features actually also show very different sources of variation. So maybe you're familiar, for example, with loss aversion literature, and we see here that actually people are quite different in how they experience or how they treat unsuccessful spot visits, but not how they treat successful spot visits. So these are interesting, I think, things to explore further. One thing that I'm not going to touch on, but just to say we're also doing this, we're also looking at to what extent are you actually paying selective attention to some individuals more than others? So of course these ice fishers, because they meet each other all the time, these competitions, so they're very well aware of their social environment. They know these people very well, and they have of course certain notions about how well their competitors are. So we had these surveys where we asked them to indicate how well they thought each of their competitors, how good of an angler they are, and then we're fitting these models, but then also looking at, do we actually see that you're actually more likely to select some individuals than others, even if these individuals are displaying exactly the same behavior. So yeah, it's not to say that these are just all the same individuals, but there are individual differences and there are social relationships between these individuals that we're now looking at, whether the importance of these relationships. Okay, and I want to switch gears a little bit. We'll stay in social foraging. I want to move to a different research question and show you a different experimental paradigm. This is work led by Dominic Defner, who also was at SciI, to Marburg University. And here, what we didn't like about the Minecraft is that it was so constrained, that it was basically with these blocks, it felt like a very unnatural way of actually structuring the resource environment. So we wanted to have something that was more continuous, that is not so block structured, but where really individuals could freely move through the environment, and then explore in more details how people make decisions. Also because these block structure also actually result in a very strange kind of movement behavior, because people have to rotate around the blocks. So it was really hard to do something directly with these movement trajectories. So we wanted to do something more natural. So we started to create this game where people have to find coins, or they have to find these patches of coins. They can't see them, so they have this metal detector. But you also see other individuals, and if you see other individuals digging, that means they found a coin field. So they actually are extracting resources, right? And so here, this individual discovered something, and once you discover it, you enter in this mini game where you then can collect your coins. We again played with two different environments, which were either concentrated, which means a few patches, so there were only 5 patches, but all of these patches contained quite a lot of resources, or the environment was distributed, meaning there were many patches, but all of these patches only contained few coins. You can imagine in this distributed environment, there's not so much payoff from joining the discoveries of others, because by the time you have joined them, that patch might actually be already empty. And then what we played with is this the incentive structure. So we either instructed people people either were paid based on how well everyone in their group was performing. So based on all the 4 individuals. Or they were individually incentivized, meaning you earn more if you do well. It doesn't matter how much the others find. And yeah, this is of course in economics. This is many different literatures. Of course, this incentivization is quite key on how what kind of strategies and individuals may employ. So here we were specifically interested. Can you actually make groups such that they stop reducing so much on overexploiting social information? Because you can imagine if somebody discovers something and everyone always comes there, that means that you're actually foregoing individual exploration of the environment, right? So that might be good on the individual level, but on the collective level, that may backfire, right? And if we look behaviorally at the results, we can see. How well are you doing as your individual success as a function of how often you are joining other individuals. And I want you to mainly focus on this blue environment. It's most interesting, I think. So this is the concentrated environments. And you see that, for individuals, the more you join other individuals, the better your success. So for you as an individual, it really pays off to look around what others are doing and actually join them in the concentrated environment. However, if you now look at what that does, what happens on the collective level of that behavior, you actually see the opposite. So here you see how many foragers there on average are on a coin field or on a foraging patch, And we see that in groups where there are a lot of individuals always on these coin fields, we see that they're collectively actually doing very poor. And that's because people are relying too much on social information. And this is kind of this classical social dilemma. It's good for me, it's not necessarily, or it's not good for the collective. A few words on, because of course, modeling. A few words on the modeling here. So what Dominic tried to do here, you can imagine, of course, this is a very different structure than a Minecraft, where you have neat blocks and which block I'm going to destroy next. Here, of course, it was much more continuous data, and it was harder to identify when was a decision made and what kind of decision was that. So we had to use a very different approach here. So what Dominic did is he tried to estimate in what kind of different state an individual is at each moment in time. The individual could be in three different states. They were either exploiting a patch, which was digging, and of course we knew when they were in that state, so that was easy. Then they could be in a state of individual exploring, so that means I'm basically walking around myself, trying to find something myself. Or they were in what we call social relocation. So they saw another individual and they decided to join that individual. So that are the three behavioral states individuals could be in. And yeah, these transition probabilities, we could estimate them directly from the data because we knew when they were in this state. But then here, of course, was the missing bit. How do you actually know when they are in which of these two states? And for that, we relied on these movement data. So you can imagine if you are in a social relocation phase, that means you're walking in a straight line to another individual. So that means your turning angle is actually very, very, very small. That means the change in distance to another individual is a bit, you're very quickly changing your distance towards another individual. And that also your relative bearing is relatively small. So basically, social relocation was inferred from individuals just walking in a straight line towards another individual. Individual exploration was based on, okay, we see people actually moving around, turning a lot, not reducing their distance to other individuals. So from these movement data, Dominic then modeled, okay, which behavioral state are they in? And then these were the hidden states. And then the question is, what actually drives people to go into these different states, right? So that was actually then the second inference problem, if you remember the intro. What actually makes them to go into certain states in certain environments or certain conditions and not in others. And so what we then find, I mean, there's more to this, but I'll keep it at this level. What Dominic then found is that, and again, I'm focusing here mostly on these blue environments, which are the concentrated resources where it really pays off to join others, because there are few patches, but they contain a lot of resources. There we see that the joining frequency in these concentrated environments is much higher, but we also see that the joining frequency is somewhat higher. It's not very strong, but it's there when individuals are incentivized at the individual level. So when they're paid according to only their own performance, the joining frequency is somewhat higher than when they're incentivized at the collective level. And if we subtract how well a group is doing compared to this collective versus individual treatment, that means that positive values means that groups do better at the collective level when also incentivized at the collective level. We see that over the time, around those 12 minutes, we see indeed that over time people are actually doing slightly better in these collective incentivization treatments than when incentivized on the individual level. But admittedly, this effect was not very large. So at the moment, we've replicated this experiment, but now in the real world. So here you see an experiment we did, where you see here one individual foraging alone in this arena. This is their arena. There's an empty arena, and here you see an arena with 4 individuals. 1, 2, 3, 4. And you can see an empty arena. Here you can see a single individual in an arena. So we always kept one arena empty, otherwise people could infer, from the behavior of their adjacent plot where maybe good places were. And again here, we incentivized these groups either at the individual level, so they were competing against their other 3 competitors in that plot, or we incentivize them at the collective level. So you say, okay, you are now as a group of 4 competing against another group of 4 on the lake. And then, of course, we're not there yet, but one of the things we will now do is, of course, is to repeat this modeling exercise and see, are people actually now changing how they use the cues to make, for example, the decision on where do I start to forage. And for us, especially the social features is going to be very interesting to us. So, do we, like in the lab environment, do we see the people when they're on the collective level incentivized? Do they actually start relying less on the discoveries of others because they want to maintain high levels of independent exploration? So that is one hypothesis that we're trying to test here. Okay, then let me move to the third topic of the day, and this is work actually led by Valerie, who's there in the back. So any difficult questions, I will happily defer to you, Valerie. We kind of, especially also inspired by the ice fishing system, where we know that these fish schools, they're not resources that are stationary, but these fish schools are actually moving. We were thinking, can we actually devise a task that gets us a bit closer to the ice fishing system, and that is that has relevance and that is interesting, has rich dynamics. Valerie did this task where people, either alone or in groups in different settings, have to track an invisible resource. And let me show you a movie. So this is a person which they have a handheld detector, and the detector tells you the quality at the spot that they are at the moment. So the higher the values, the redder, that means the better that location is. And the closer to 0 or even 0 means I'm actually not very close to the center of the resource. So you here have your personal information. How good is my spot? And you don't see the resource, so the resource is actually it's mobile under you. But you also see other individuals here, right? So you actually also see the location of other individuals, and these are groups of 5. And again, each individual is another human being that is doing exactly the same task as you. And this also actually was an online experiment that I think was really cool. That Valerie developed this during his master thesis, so it was hugely impressive on many areas, many different ways. We had different treatments here. One of the treatments was that you actually saw also the quality of the location of other individuals. So by the beam, so the color of the beam actually tells you how well is the location of the other individuals that are in my group. So the different conditions we had individuals were either doing this alone by themselves, so not in a group setting. Then the first video I showed you, they did see other individuals, so they were a group of 5, and they could see other individuals, but could not see their payoffs. Then we had the last condition I showed, where everyone is signaling all the time the quality of their current location. And then we had another treatment, which is the voluntary sharing condition, where people could decide whether they want to signal or not. So we want to see the dynamics of when do people actually decide to share information about resource environments. And I mean, I won't have time to go into all the details, so I'll just give you a glimpse. One, I think, quite interesting result that Valerie found is that when we look at situations where all 5 individuals are not on the resource, and then one of them finds the resource. So we're here looking at certain events that are happening. Then we can, of course, ask what happens during these stages where no one is on the resource, then one person finds that. How does it actually change then certain dynamics? And here you can see what happens to the in degree of that individual who discovered it. So the in degree, so how much visual attention or other people paying to that individual. And here you see that separated out for the 3 social conditions. And so here T0 means that's really the moment where that individual enters this discoverer enters the patch. And we see that in this all payoff condition, so where you can see the payoff of everyone, we see that this individual very quickly draws a lot of social attention. So a lot of eyes are turned to that individual, right? When there's no payoff information, this is actually not happening at all, right? So somebody found a resource in your group, but of course there's no way for you to know that, right? It could of course be that they change certain movement characteristics, but we don't see any evidence of that. And then the voluntary payoff is somewhere in between. So it suggests that there's some benefits of asking people to signal as compared to having no payoff information at all, but it stays far away from the all payoff condition. Then Valerie wanted to understand, can we understand how they decide to actually move in this environment? So we developed a computational modeling of rotation. So people always continuously have to decide, am I going to go straight? Am I going to go to the left? Am I going to go to the right? And you basically have to make this this decision continuously. Although it's a question in itself, at what resolution are individuals like making such decisions? Valerie derived an optimal rotation model, and the optimal rotation model is relatively straightforward in the sense that if you see that your meter value is increasing very rapidly, then you should just continue straight because you're moving towards the resource center. It's probably something I should have told. I missed. So the resource is a circular patch, and the best quality of the environment, the best quality is at the center of the patch. So the center is best, and then it towards the edge of the resource it becomes less and less. So when my meter value sharply increases, I should continue straight. If my meter value sharply decreases, that means I'm moving away from the center of the resource. So then I should actually make big rotations. I had a look whether indeed this is what people are doing. So are they actually rotating as a function of the change that they see in their detector values? And we see that indeed in all conditions that is happening. Most strongly in the alone condition, which makes sense because in the alone condition, that's all the information you have. You only have your meter, right? There are no other individuals. We see in the social conditions, we see that the individuals start paying attention to what others are doing, probably. And then, of course, we can also look at how the position and perhaps the behavior of other individuals are affecting how you are rotating. And here, Valerie found that, for example, where other individuals are is affecting where you're turning to. Also, in which direction that they move, but much more stronger so in the all payoff condition. Which again, I think it makes sense, right? Because you have much richer information to orient yourself. And also, in this all payoff condition, people would really infer, or they would turn more strongly when they saw individuals that were at high payoff locations as compared to individuals that were on low payoff locations. And that was not present in these other conditions, again, because you could not actually discriminate how well the location was of another individual. And trying to kind of like get at something similar, or at least related in the real world, we are really trying to understand the movement dynamics of these and the buildup of these clusters of individuals. So in this ice fishing, we regularly see that really people come together. There are really larger and larger groups building up till that group actually moves, and then at some point that group disintegrates again. And one question you may ask is like, what are actually the features that drive the increase or the disappearance of these clusters? Relatively preliminary, but what kind of this hints at is that that clusters increase in size when the density of individuals, so foragers, is actually relatively high. So when they're sitting compactly together, it seems to then lead to increase in the cluster size, so the number of individuals, and also when the catch rates are higher, that also seems to lead to a survival or longer survival of such a cluster. For example, size. Size. Like the larger, the more likely you are to collapse, which is somewhat trivial. And of course, then one question you may ask is like catch rate. So does it mean that other individuals looking at that cluster can actually see the catch rates happening at that moment, and when they see high catch rates, they're actually more likely to join that cluster, right? So it becomes a more fine-grained question of what kind of social cues are being used, right? Is it only the presence of other individuals, or is it actually how often they take out fish that people are inferring and keeping track of, right? So that's one possibility, right? But the other possibility is that high catch rates simply means that nobody's leaving the cluster, right? Everyone's staying, so that therefore the cluster actually remains. And that seems to, this latter information seems to be, this latter possibility seems to, there seems to be more evidence for that. So it seems that if you look at the catch rates, you see that at very high catch rates, the likelihood of the cluster to contract, so to reduce in size, is actually very small. So that means it seems as if people are just not leaving. Whereas if catch rates are relatively low, we see that there's a larger likelihood that people are leaving and that the cluster is collapsing. Whereas for these other two processes, there are some hints of it, but seems not to be as strong. I think one like future goal here is to also understand more actually the dynamics of how these clusters actually move through space. Right, so we see when there's a cluster, we see actually a lot of small-scale displacements of one individual packing up and then relocating 10 meters further, but still staying within that cluster. And here you see simulation of one of these clusters, and if I remember correctly, red means a catch, and blue means there were no catch in that selection. And what is really interesting and is that Valerie also tries to estimate also where are the fish actually, and based on the catch rates, right? So I have not touched yet on where what is actually the resource doing, but here of course you can based on where individuals are catching in the cluster, you can try to at least have a rough prediction of where the center of, for example, the fish school actually is under the ice, and to what extent is a collective then actually able to track the center of such a fish school, for example. Parallel to that, we're also trying to use underwater sonar to directly quantify fish densities. This is certainly one of the harder aspects of this whole project. I'm showing you here one very very nice illustration of how sometimes it works very well. So here we see a school of fish. These are actually fish, these stripes. I think here you see actually the lure of an ice fisher going down. This is really the lure that's being lowered into the water column. And actually here you see attraction of the fish to the lure. So the fish are actually moving towards the lure. But this is certainly not, we haven't gotten as far yet as I'd hoped, because it's actually, it's not easy to handle these sonar data in these conditions. Yes, I think that's 1 hour. Shall you spend 5 more minutes on this, or shall I leave it at
5 minutes? Is
5 minutes, yeah. Then very quickly. Fourth part, but I'll keep it very brief. Is can we understand a bit more on a mechanistic level how people actually learn in social foraging environments? And here we developed a game where people have to decide which pond am I going to fish. And again, these are groups of 6 individuals. Each person is playing an avatar, and you basically have to decide which pond am I going to. And start fishing. The information you get here is your when do you catch a fish. So you get continuous personal payoff information about how good that lake is. But you also see other individuals, and again we did different iterations. Here you, for example, see. So here, for example, in this version, you see the presence of other individuals, so you see where they are, but you're not seeing when they're catching fish, right? So you don't have direct information about how well they are doing, but you see how they are distributed, or they can see how you are distributing. And again, here we also play different iterations different kind of features available to decision makers. Here it's the first time that we start using, for example, models like reinforcement learning. So how are you learning from your own personal rewards, and how are you learning from, for example, the distribution of other individuals, right? So if you see more individuals in another location, to what extent are you weighing that in deciding how long you are staying somewhere, or which position you're moving to? In parallel to that, we're also trying to employ evidence accumulation processes, which is a very different class of models, and to really understand, when is your decision triggered to actually leave a patch, right? So you can imagine if you catch a lot, that actually your likelihood of leaving is always reset to 0. And then over time, you're more and more likely to leave unless you catch something, or maybe unless you see more other individuals that are in your patch, right? So here we can again try also to tease apart the contributions of personal and social information. And finally, we've been looking at the giving up dynamics in the field. So how do people actually decide how long do they stay at one location, right? So that's of course next to where am I going, how long am I staying somewhere is also a very important point. And what seems to be kind of the main determinants here is that the longer you go without any fish, the more likely you are to leave, which is of course unsurprising. But this kind of baseline tendency of leaving actually gets lower once you catch a fish. So once you caught a fish, you're overall less likely to leave that place. And then kind of the same story continues with the longer it takes that I didn't catch a fish, the more likely I am to leave. There are some more fine-grained results here. We can also discuss if you like. And then, for example, what we find is that social density, again, to some extent actually modulates these patterns. If you're fishing in an area with other individuals, you're actually a little less likely overall to leave that place, given the same personal information, meaning fish catches coming in. Okay, so like I started, I think the kind of what is all happening in terms of development, the technological and computation modeling really allows us to study the role of cognition in the real world more and more. I want to thank lots of contributors. I mean, we did a massive amount of teamwork. I'm just telling the story here. And thank you all for your attention.